So last time, some of it's still on the board, I guess. We started talking about more specifically what anti-de Sitter space is. So we defined it by embedding it in a higher dimensional space so that it makes manifest this SO2 comma n minus 1 symmetry. And we found there are sort of two coordinations. One is called global coordinates and one is called Poincare coordinates. So this is Poincare coordinates. I'm going to switch notation, I think, a little bit from what I did yesterday, where I was calling these y's. I'll call them x now. And these are basically what you should think of them as the field theory coordinates. Your homework was to show that massive particles do not reach the boundary at z equals 0. But massless particles do in a finite time. So what I had in mind was just looking at the geodesics. So you look at null geodesics for massless particles, and then you look at time-like geodesics for massive particles. Null geodesics are easy. Let's just take things that don't have any momentum in the transverse direction. So then you're just looking for ds squared equals 0, which is so paths like this. So then that just tells you z dot squared equals 1. Obviously. And so then these are just straight lines in the zt plane. Obviously, they're not actually straight lines because of the curvature.
Is that dt squared, right by dz squared? Okay.
It's good?
Yeah.
Okay. So then if you're at some point in the interior of AdS, and this is the boundary at z equals 0, I'm drawing z increasing this way to remind you that this is sort of radially outward. Z is like 1 over radius. Then it's just a straight line like this. And so if this is a coordinate distance z equals L, then it takes time L. Okay. For the time-like geodesics, you have to do a bit more work. You can either just write down the geodesic equation by finding the Christoffel connection, or you can start with that. And then you'll find sort of exponential-like or Sinch and Koch-like trajectories in the zt plane, where they'll never quite reach. So it'll look something like this. Or you can write down the action for a relativistic particle, which, and then switch to Hamiltonian formulation, define a canonical momentum, go to Hamiltonian, which is conserved, and then show that it would take infinite energy to reach the boundary. A third way, which is related to that, would be to use the killing vectors, which I'll come to in just a moment, and show that there's a conserved quantity along the geodesic trajectory. Okay. By the way, why it's a little one other point that I should have emphasized is that the proper distance, the physical distance from any point to the boundary is infinite, right? Because that's going to be like dz over z. So it's log divergent. Right? So the fact that light reaches in a finite time is surprising. But it's because time is warped in the same way. Okay. So I'll skip that. Okay, so then what are the isometries? How do you understand this SO2, 4 symmetry that was obvious when we embedded it in this higher dimensional space in Poincare coordinates? Okay. So by isometry, I mean you do a coordinate transformation that leaves the metric in the same form. Okay. And if you talk about the infinitesimal version, then that's what's called a killing vector, which is you take your coordinate x mu, you go to x mu plus xi mu, and to leading order, the metric is invariant. The way to think of this is in sort of a gauge theory language is that these are sort of defective gauge transformations where you tried to do a gauge transformation on some particular background, and then nothing happened. Nothing actually changed. Okay. So what are the coordinate transformations like of this form that leave the metric invariant? Okay. Can anyone tell me one? Some of them are pretty easy. Sorry? Yeah, so all the Lorentz and Poincare actually for the field theory directions are there, okay? Because those killing vectors leave this part of the metric invariant and they don't do anything with the z coordinate. Okay, so you have translations in del mu, and you have rotation slash boosts, x mu del nu, x nu del mu. What's new is you have a sort of radial symmetry, which for reasons that are obvious, I'll call it dilatation, where you do z del z plus x mu del mu. So that means you take so this is basically a scale transformation. The finite version would be you take z to some constant lambda times z, and you take x mu to lambda x mu. And then you can see that overall this whole thing gets a lambda squared out front, but then because there's the 1 over z, that cancels out. Okay. Leaves the metric invariant. And then I'll just call them special conformal transformations, which is obviously hinting at where things are going. They take a bit more work to find, but they take the form where x squared here, I mean the Minkowski dot product, obviously. Okay. So there's one, mu is a free index, so it's kind of like a translation, or a generalization of a translation. We'll talk about what it is in the field theory in a second, or in a few minutes, actually. Okay, before leaving AdS, let's look at the wave equation for a massive scalar in AdS. So that is take action, something like, and in general I'll be talking about AdS d plus 1 because that's sort of natural if you have if we're going to be dual to a d-dimensional CFT. So we take this as our action. The wave equation is just the box in AdS. Where this is 1 over root minus g in general. Let me use lowercase Latin for all the directions since I'm using Greek for the field theory directions. Okay. So phi, I guess, here. Yeah. Okay. Comment. In AdS, it's actually possible, or it's consistent to have tachyonic masses. These don't lead, as long as they're above this value. This is called the BF bound, or for Brighton, Lohner, and Friedman. I always say BF because I can't ever remember how to pronounce Brighton, Lohner. Basically, the curvature of AdS sort of acts like a positive mass correction. So even though this locally looks tachyonic, it's stable and doesn't have any problems as long as you're above this bound. Okay. So if we just plug in with that metric for a box here, then the equation we get is z to the d plus 1 del z, 1 by z to the d plus 1 from the root g's, z squared from the inverse metric del z phi, and then plus z squared, and then I'll call it box tilde for the Minkowski box. Okay.
Again, how do you get this equation?
From here?
Is that from that?
Yeah, so this is our metric. So
G.
I plug in with root g. Okay. So I'm going to be working in AdS d plus 1. So that means there's going to be d plus 1 z squareds. And so I have square root of that, so then I just get z to the d plus 1. So that's my root g here and here. And then the inverse metric, so g upper zz is going to be this component inverse, so then that gives me the z squared. So I'll frequently set L equals 1 for simplicity. Okay, so just measure things in AdS units. And then same thing here, I just get a z, the root g's cancel here because there's no z derivative, and then the inverse metric just brings a z squared. Okay. So then this is supposed to be m squared phi. So let's separate variables. If we want to study this equation by using the symmetry, so we'll have a function of z, and then we can just Fourier transform in the transverse directions. And then the equation of motion you get takes this form. Which you can solve. It's almost a Bessel differential equation. So with a little work, you can massage it into Bessel functions. So what is, or actually, I'm sorry, this should be, no, I'm sorry, not a Bessel. This will be a 2F1, I think. Anyway, what we'll be interested in right now is what's the behavior near the boundary. So near z equals 0. Okay. So if this were the wave equation in flat space and you asked this question for large r, what is the behavior, then you would find that it's an irregular singular point. Yes?
Sorry, I'm confused. Where is the second area of equation?
Here, double prime.
Oh, it's double prime.
Yeah. Is that clear now? Okay. I can try and write a little bigger. So in flat space, if you did the analog of this, then you'd find that it's an irregular singular point, which corresponds that you have this exponential e to the ikr type behavior. Here, it's a regular singular point, so you can use your Frobenius method, that is just a power series. Yeah?
So when you're saying EIKR in flat space, are you talking about the radial coordinate?
Yeah.
Okay. I just...
Right,
okay.
yeah. So we can look for a power series solution. So for small z, yeah, we multiply through by z squared. And this, so k drops out. And I forget what this polynomial is called, but you put in an ansatz alpha z to the alpha. It's like the characteristic polynomial. It has a name. Anyway, you look for the leading power. And you get this quadratic equation. And you find I'll put L back in here.
Are you assuming something about the z? Why does k squared drop out?
I'm looking at the behavior near z equals 0.
Right, so you're assuming fz is also smaller.
Well, it's a general, if I look at this differential equation, then I see that for small z, the coefficient, after I've put it in canonical form by making this 1, the coefficient here goes like, is a simple pole, 1 over z, and then for the leading behavior here is 1 over z squared, so then that tells me that this is actually a regular singular point. So that tells me that solutions have to take the form z to the s, or alpha. That should be n. So this is a Frobenius method. And so now I'm looking for this power alpha. So then I solve this equation. Right. So this will be an important equation, and also solving for alpha in terms of the mass. There's obviously two solutions. So that tells me that near the boundary, phi, so there's going to be, it's a second order differential equation, so I'll have two solutions, which I'll call phi 1. So this is general, of course. But then near the boundary, one of them will behave like z to the alpha plus, and one of them will be like z to the alpha minus. And when we're not in this sort of weird tachyonic situation, then one of these is blowing up as z goes to 0, and one of them is falling off. So one of them is like going like a negative power of z, and that's blowing up.
Excuse me, why did you say the tachyonic solution is not really a problem?
Why is it not really a problem? So that requires a more careful analysis, which I don't really have time to go through, but there's not a stability problem you can show. Sort of morally, the argument is that the curvature of AdS sort of acts as an extra mass term. And so that's what this factor is. So that sort of loosely, if you go to like you can sort of go to like a Hamiltonian description and see that the Hamiltonian gets an extra constant piece that's makes it positive definite.
Basically, from the solution, just that equation basically says that the square root has to be real as opposed to imaginary.
Right. Yeah, that's consistent with that. But that's right. There's a more refined argument, which is why it's called it's named after these two people that argue in their paper. And that was actually work long before AdS Cft, showing that you could have these masses. So let's see, as written, alpha plus will usually be a positive power of z. So this will be going to 0 near the boundary, and then this will be a negative power, and so that will be blowing up as z goes to 0. So typically, you want to choose boundary conditions on AdS where this is 0. So you want things falling off near the boundary. Okay. So if you have this being non-zero, then it acts as a source in the CFT, and that's what we'll want to be doing. But in terms of the boundary conditions, you think if you just have the AdS space and you're studying dynamics, then you want this to not be there. So you should think of this kind of term as acting like a source, and this is being the response. Okay. One last thing about AdS that I wanted to actually was sort of the point of this discussion about things reach the boundary. So the point is that if you're at some interior point of AdS, you shine your flashlight radially outward, and some finite amount of time, your light ray reaches the boundary of AdS, and so you have to say something about what happens. Does it get absorbed? Does it get reflected? And so the point is you must put boundary conditions on AdS for it to make sense. And so it's more like a box. So people frequently say that AdS is a box precisely because you have to put these boundary conditions for the massless fields. And it also behaves like a box because the AdS scale actually works as an infrared regulator for the field theory in AdS. Okay. Any more questions about AdS?
Yeah.
Yeah.
If I were to think of the analogy of Euclidean radial coordinates, then I'm not so concerned about what happens at R at infinity.
Mm-hmm.
Why should I be so concerned about boundary conditions at z equal to 0?
I think I thought I just told you. Because things can reach there in a finite amount of time. So, so like if I shine my flashlight, then I have to give you boundary conditions. Otherwise, the physics up here is totally undefined, right? Because my light ray has reached the boundary. So does it reflect or did it get absorbed? So is this guy going to see a flashlight or not? So obviously that's not true. Like in flat space, it takes infinite amount of time to reach the boundary. Okay. So that was the left-hand side of duality, what we'll need to say about AdS for now. So what about the right-hand side? What is CFT? So it's a quantum field theory that has a conformal invariance. Why might you be interested in studying these? So there's, under various assumptions, if you have scale invariance, so that would mean that you're at the fixed point of some RG flow, for example, and Poincare, and unitarity, and then it's unclear what other ingredients are really required, but quite generally, you get the full conformal invariance. Okay. That I'll describe in a second. So basically, when you reach an RG fixed point where your beta functions vanish, you should expect that theory to be a conformal field theory. So it's sort of an open problem to figure out exactly when this is true, although there are no interesting counterexamples. In 2 dimensions, there's a proof. In 4 dimensions, it's a little fuzzier. So what's sort of the most symmetry that you could have? Well, it's the symmetry of the kinetic term. So let's just talk about if you talk about a massless scalar, and now we're working in flat space in d dimensions. Well, I'll leave it like this, but this should be the flat space metric. Then you can ask, what are the local symmetries of this action? So there are the obvious ones, the Poincare symmetry, but there are more. So before we were talking about coordinate transformations that left the metric the same, or left the metric invariant. But you could also ask about coordinate transformations that leave the metric in the same form up to a multiplicative factor. Okay. And because the equation of motion is just the DL inversion, you can see that if I do one of these coordinate transformations where G just goes to, the metric just goes to constant times the metric, then the equations of motion are invariant, and indeed the action is invariant. So for the simplest example is scaling, as we mentioned. So you take your coordinate x mu to some constant times x mu. And you scale phi with its scaling dimension. And then this is a symmetry of the action. Because you get an omega to the d from the measure, you get a 1 over omega squared from the derivatives, and then you get an omega 2 minus d from the scaling of the field times s. But the conformal group is more than just scaling plus Poincare. There's another example of a transformation that is a symmetry, and that is inversion. So x goes to L squared over x, basically. There's not any infinitesimal form of this transformation because it's not connected to the identity. But this is also symmetry of this action. And what we can do is we can do an inversion followed by a translation, an infinitesimal translation, and then do another inversion. And this is what's called a special conformal transformation. So just counting the symmetries, I have translations. In d dimensions, I have d of them. I have rotations and boosts. So that gives me d minus 1 over 2. And then I have my dilatation, or scaling. There's just one of those. And then I have a special conformal transformation for each direction I can translate. So then that's another d. If you add them all up, you get which is d plus 1, d plus 2 over 2, hopefully. Yep. And moreover, you can write down the generators and work out the algebra. And you'll find that this is SO2 comma D symmetry, which is consistent with that counting, right? So the generators given by this. So you can see that these look very similar to these killing vectors in AdS, and that these coordinate transformations in AdS induce exactly those transformations on the boundary at z equals 0. That's why I labeled them as I did.
Which is one correspond to Spatial conformal transformation here.
This one, this one here.
I mean,
The last one,
oh,
right?
this is the last one.
Yeah.
For that one.
It's the same.
Yeah, hopefully I got that. Yep. Up to a minus sign or so. Yeah. So how do we organize our fields in a conformal field theory to make use of this enhanced spatial symmetry? So in terms of labels, or the Cartan subalgebra, we'll have the usual momentum and spin. So momentum, spin. But now we'll also talk about a scaling dimension, which is usually denoted delta, which is the eigenvalue of the dilatation generator. So that's how we label our states or the operators. But we want sort of to talk about multiplets. So what you can show is that the algebra is such that the special conformal transformation generator acts as a lowering operator for a conformal dimension. By 1 unit. And the momentum generator, or the derivative operator, acts as a raising operator for the conformal dimension. Okay. So if I have some field with conformal dimension delta, that is to say, it transforms like this under a scale transformations. So, and unitarity will demand that delta has to be positive, and that delta equals 0 should only be the identity operator. So that means that I can keep applying k until eventually it has to annihilate the state. And so I'll call those the lowest dimension operators. And those are sort of how I'll label my representations under the conformal group. And so those are called primary operators. So then what I can, the correlation functions in a conformal field theory, because of the conformal invariance, will be entirely fixed by their primaries. So then I can just look at the conformal the correlators of primaries and then compute all the descendants by just taking derivatives, essentially.
So doesn't that be D the operator equal to 0? I thought delta was the eigenvalue of D.
Delta is the eigenvalue of D. K is the lowering operator for delta.
Oh, but that's not the lowest state then, that's the state.
No, this is the
state that's then annihilated to.
so O is a primary operator, or its corresponding state. It will have some dimension. Let's call it delta naught. But k on this is 0, so that's telling me I can't lower the dimension any further. So this is a lower bound. I can apply I can apply p's to raise the dimension and find all the descendants of the primary language people use. I should mention that when you start talking about these operators in conformal field theory, I'll be descending. I'll talk about like descending with p, which is like the derivative operator. So these are not. These are not like the fields that you integrate over in a path integral necessarily. These are just a collection of all the operators that I can have in the field theory. Okay. So and obviously there are entire courses on conformal field theory, so I'm just giving very basics. So the first thing that one usually shows is that if you have two primary operators and you take their two-point function so first of all, from Poincare invariance, you know that the two-point function has to be just some function of the interval between them. But conformal invariance tells you more. In particular, this has to be the form, if this is operator 1 and operator 2, that I can choose a basis such that in general, there's some normalization here. So I'll normalize my operators. It's conventional to normalize them so that it's a unit over the separation there. And then all descendants will be fixed. So this is by just taking derivatives. For three-point functions are also fixed. So there'll be some constant, and now this constant has intrinsic meaning once I've normalized my fields like this, where it's the 1-2 separation to delta 1 plus delta 2 minus delta 3. These are for spinless fields. It's more complicated if you have spin. And then this is delta 2 plus delta 3 minus delta 1. And then cyclic, so delta 3 plus delta 1 minus delta 2. You find these constraints just by basically using the special conformal and the dilatation operators. You get some differential equation for the correlator, and then these are the solutions.
For the two-point function, why do you only have 2 delta 1? Or is it just they're the same?
Because different primaries will have vanishing correlator. That's what this Kronecker delta means.
Right. Okay.
So I could just put delta 1.
Then it's
Yeah. The 4-point function is constrained by conformal invariance, but it's not completely fixed up to a constant. But you have a function there. Okay. The other nice thing that happens for conformal field theories is that the operator product expansion, which does exist in general field theories, although it's usually an asymptotic expansion, it doesn't have nice analytic properties as I understand it, becomes very nice for conformal field theories. In particular, it has a finite radius of convergence. So I'm being schematic here. I hope you all can figure out what I mean. But it allows you to take a product of operators and rewrite it as a sum over operators evaluated at one point. So these are at two different points. This should be 2, obviously. And then x1 minus... And so, in principle, this operator product expansion allows me to compute any correlator with enough effort, because I can just take like an endpoint correlator and then start using the operator product expansion with its finite radius of convergence to write it as in terms of n minus 1 point correlators, and then reduce it down to 2-point functions. Of course, that can be a difficult computation in general. So notice that it becomes, typically this will be a Laurent expansion. Yeah, and here, yeah, okay. So this coefficient is the same as that coefficient. Okay, so then that is to say that we can define a CFT not from a Lagrangian, but axiomatically in terms of a spectrum of operators So a set of operators and their spectrum, meaning their conformal dimensions, their scaling dimensions delta. So I mean primary operators. And their 3-point functions. So their OPE coefficients. So if I have this CFT data, then that suffices to compute all correlation functions and can serve as a definition of conformal field theory. The caveat is that not every set of operators and OP coefficients that I could imagine writing down is actually going to be a consistent theory. And so figuring out what the constraints are is what the conformal bootstrap program is. Okay, but that's, I think, all we need about CFT for now, unless there are some more questions.
So does it mean there is sort of no like particle interpretation of the correlation function of exponential?
There doesn't have to be. Yeah, there's not going to be nice. The correlation functions are not going to fall off rapidly, so then defining asymptotic states and like a scattering matrix, technically you can't do it unless you break conformal invariance in some way. Because there's no scale, basically there's no scale in the problem, so stuff just has to fall off like power laws. But like in n equals 4, people do talk about an S matrix. And so what they have in mind is breaking the scale invariance in some way. And exactly how they do that, I would have to look at the literature to clarify that point. But yeah, that's a good point. So I think now we're sort of ready to start talking about how to identify the two sides of the AdS-CFT correspondence. So some basic entries in what's called the AdS-CFT Dictionary. So the idea is that we want the CF. So first of all, as should have been clear, the AdS space had this SO2, D isometry, and then that's exactly the SO2, D conformal group. And when I wrote down the killing vectors, you could even see roughly how it acts on the boundary, and that those are the same transformations. And so the idea is that the CFT lives at the boundary where I had to put those boundary conditions. And because when z goes to 0, the whole metric blows up, I usually, for calculations, I have to put it at some cutoff. So I have an epsilon behaves like a UV cutoff in the field theory, although I'll talk more about how to understand that. So remember that AdS had this isometry. Z goes to omega z, x mu, goes to omega x mu. So this was in AdS. On the other hand, in the CFT, my operators have this kind of scaling. So if I remember, we just looked at the asymptotic behavior of scalar field in AdS. And we found that the solutions behave like powers of Z. So suppose you have some field phi in AdS. Then near the boundary, it was like z to the alpha times some function, which I'll call phi naught of x. Okay, so near boundary. So if I do this kind of scaling, then obviously it goes to omega times the alpha, omega to the alpha, z comma x. So alpha, that power law, is looking like the scaling dimension in the CFT. So it suggests we make the following definition, that we can define an operator in the CFT at a point x as a limit. So there's going to be some normalization here. So then alpha is the scaling dimension of the CFT. So this should just be phi naught. So recall we had this equation that I said was important, that the mass squared was alpha minus d, so that becomes delta minus d. And so then this is telling us about how conformal weights in the boundary are related to masses of particles in AdS. Okay. So roughly this is what Maldacena had in his first paper. And I think people didn't really know how to use it at that point, or that's what I'm told. I wasn't really active then. Until Witten made the following conjecture, which was how to identify the generating functional of the CFT correlation functions in terms of the AdS. So he claimed that this is equal to the partition function in AdS d plus 1, or specifically it was in the context of n equals 4, so then that would be AdS 5 cross S5 of type 2 super 2b string theory. But with, so here phi naught, on the left-hand side, phi naught is like our classical source that I take functional derivatives with to find correlation functions. So on the right-hand side, that'll just be my boundary condition, so that if I have some field phi of z comma x, then when z goes to 0, it should go to z to the d minus delta, this is delta, times phi naught, as z goes to 0. So remember I had those two terms when I solved the equation, 2 powers. So the one that blows up, that's behaving as a source in the partition function for the CFT on the left-hand side. So because I'm putting this thing basically in the action, it has to be invariant under all the symmetries. And so if O has a dimension delta, then phi naught had to have dimension d minus delta. And it must be a singlet of all the other symmetries. So that allows you to start identifying fields in AdS with operators in the CFT. So, okay, in 2 minutes I can't do the 2-point function.
We can continue next time.
Yeah, but what I was going to start doing is saying that if you take n to be large and you take lambda to be large, then this right-hand side becomes supergravity, and it becomes classical supergravity, so I can use the saddle point approximation, and then I should just think of this as e to the minus on-shell action. If I get, I'm writing this in Euclidean, if that wasn't obvious. So the on-shell action will be some function of my boundary conditions. And then I can take functional derivatives with it to find correlators in the CFT for large n and large lambda. But that'll have to wait till tomorrow, I guess.